Alright, so in this video, we're going to be looking at the boiling point of water. And it actually takes a really long time to boil water, so I'm going to start heating it up already. So we're going to boil water, and theoretically it should boil at 100 degrees Celsius. But, you know, it's not pure water, it's tap water, and I'm not sure if I have the most accurate thermometer, so we're going to test it out. I will put the thermometer in when it's boiling. We'll see what it is, so that we can kind of calibrate our reading to see how it changes. And then I want us to take a look at how the boiling point is going to change, whether we add a little bit of salt to the water, or if we add our sugar to the water. So we're going to be using those same two things, mainly because sugar and salt are extremely common. You probably have in your kitchen. And we eat it. We need both of them in our diets to survive. Well, I guess not sugar, but you do need some amount of salt in your diet to survive. So I will skip forward to when it's boiling. Looks like it's just starting to boil. We're going to wait till it's at a full boil. So all the water will be that same temperature. I just want to review a little bit with you guys about how intermolecular forces interact with boiling point. So it's usually the stronger the attraction, the stronger that intermolecular force, the higher that boiling point is going to be. So I want us to think about how, we'll do salt first. I want us to think about how salt and how those sodium and chlorine ions are going to interact with the water, and whether that might increase attraction or decrease attraction, and how that might change the boiling point. Let's take a closer look at what's going on when salt and sugar dissolve. We'll take a look at sugar first. So sugar would have a bunch of other sucrose molecules all around it, and water comes in and it kind of grabs onto, or it hydrogen bonds to these things instead of the other sucrose around it. So they all get broken down into individual sucrose molecules, which then float around, which is very similar to what you see in salt. But instead of getting broken down into molecules, in salt, it will get broken down into individual ions. So the salt has a very strong partial charges. You'll see the sodium plus ions will be surrounded by, and I could write these down here, our oxygen, which all have partial negatives. So that's why they're attracted to each other. And the negative chlorine ions would have the positively or partial positively charged hydrogen surrounding it. So this is what salt water would look like. And there'd be a lot of more water molecules all around. All right, we're at a full boil now. Let's take a reading on our thermometer. Go to Celsius here. Leave that in there. Looks like we're at 9. Wow, accurate thermometer. Look at that. 100.2. 100.0. All right, right on. That's exactly what we would expect with water. So this is the most accurate thermometer I think I've ever used for this. All right, so I already poured my salt in here. So this is NaCl. I've measured out about 100 milliliters. So I'm going to mix that in, and we're going to see what our boiling point becomes. So It should stop boiling because the salt's a little bit cooler. We'll mix it right up. And wait for it to boil again. All right, all dissolved in there. All right. All right, we got a light boil. We're gonna wait till it becomes a real nice heavy boil here. All right, that looks like a heavy boil. So I'm going to shift it this way so you can get a better look at the thermometer reading. Whoops. And it looks like we're at... Oh, you can't see it. Looks like we're at 102.3. Let me see if it changes if I go somewhere else. I want to be very careful not to touch the bottom of the pot because that'll be a different temperature than the water. 102.4, 102.3. Probably right in there about 102.2 or 102.3, 102.4. So that's what we got. All right, I cleaned out the pot. We're gonna use the same amount of water again, bring it up to boil. This time, we're gonna be using our cane sugar to see if that boils at a higher temperature, a lower temperature. We're gonna see how those intermolecular forces might be a little different with sugar and how that affects boiling temperature. All right, water just started coming to a boil. It's always good to just double check to make sure. This should be about 100 exactly. It was last time. Just make sure our thermometer is still working well. All right, don't want to burn my fingers. All right, so it is 100. I already measured out our 100 milliliters of sugar. We're gonna place this in right now, mix it in, see how that changes our boiling point. All right, so that's, make sure I get all of this. We'll mix that in there. And think of whether this will be higher or lower than just regular water. Think about where this might be when thinking about salt as well, salt water. All right, looks like it's all dissolved in there. We'll wait for it to come back to a roaring boil. And we will take a look at the temperature. So just a reminder, with pure water, we're hitting exactly 100. With salt, it was about 102.3, maybe 102.4. Looks like it's boiling pretty well again with sugar. Give it a little bit more time maybe. Alright, and we will take a look at what the number is here. So right now I'm reading 100.2, 100.3, 100.2, 100.3, 100.5. I'm gonna burn my fingers here if I'm not careful. All right, let me get a hot glove on here. See what we can get. Hundred point two, 100.3, back down to 100.2, 100.3. All right, that looks like what we're gonna get, 100.2 to 100.3. We'll give it 100.3 on that one. All right, so now that we got our results, let's think about what we expected and what ended up happening in terms of intermolecular forces. So here's our results from that lab. Our water boiled at 100 degrees Celsius. When we added sugar, the boiling point was 100.3 degrees Celsius, so a little bit higher. And when we added salt to the water, our boiling point was 102.4 degrees Celsius, so even higher. So let's take a look at our intermolecular forces and what was going on. We could take a look at water first. So if we just had water here, let's throw some water molecules up here. We got a bunch of hydrogen bonding going on. So the partial positives are going to connect to the partial negatives. And it's a liquid, so they're moving around, but you know, they're still kind of attracted to each other. There's a intermolecular force attracting them. And when it hits boiling point, that's what needs to break, these intermolecular forces, so that they boil off. So they're attracted by hydrogen bonding. So if we take a look at sugar, it's a much larger molecule and it has a lot more spots to hydrogen bond. So the water can surround it and can bond to the sugar very well. And that is a very similar bond to, you know, water molecules right here. But it's enough to increase the boiling point by 0.3 degrees Celsius, which means it increases the attraction just a little bit. So it's holding on to those water molecules and the sugar molecules. They're holding on a little bit tighter than just the water by themselves. And then lastly, when we added some salt to the water, what happened was water broke it apart. The partially negatively charged oxygen would pull the sodium ions apart from the chlorine ions, so that partial hydrogen would pull at the chlorine ions. And the water would, you know, kind of cling to these ions, because these ions have full charges. So you might see something like this. And these full charges will be holding on very, very tightly enough so that the boiling point goes up. So we need even more kinetic energy. We need even more speed of those particles for them to break apart into a gas. So to conclude, we can know that the attraction between our fully charged ions and the partially charged water molecules will be stronger than the attraction between our water molecules and our sugar molecules, because it took more energy to break those intermolecular forces and it to become a gas. So that's what boiling is. It took more energy to break apart those intermolecular forces.